Welcome back to Real Number System. In the second part of section 2.2, we're going to talk about cardinal numbers, we're going to talk about the universe and Venn diagrams, and we're also going to talk about subsets. So let's get started. First, we have what a cardinal number is. A cardinal number tells us how many elements are in our set. You'll notice we denote the cardinal number as n, open parentheses, and we write the set name, the letter that we use to denote the set, in those parentheses. So the question asks us, what is the cardinality of each of the following? So we write n, and we put the k in parentheses. I count how many elements are in k, and there are 5 elements. So the cardinality of k is 5. For the next example, we write n, and in parentheses the L. This set has only 1 element, and so this one has a cardinality of 1. We talked in the last video about equivalent sets. Well, equivalent sets have the same cardinal number because they have the same number of elements, if you remember from our definition. Well, equal sets have the same cardinal number for the same reason. They are exactly the same, and so they have the same number of elements, which means they have the same cardinal number. It is also possible for a set to have no elements. Its cardinal number would be 0, and it is called the empty or the null set. The symbol that we use to write the empty set is a 0 with a slash through it, or you might write it with the braces here, with nothing in them. Now be careful with notation. The null set never will have the braces around it. If you have the braces around the empty set or the null set, that is actually a set itself. It's a set that contains the symbol of the empty set. So the braces around 0 does not mean the empty set. This particular set contains 1 element, which is 0. So just be careful with that notation. That brings us to our next topic, finite sets versus infinite sets. It's related to our cardinality. A finite set is the set of whole numbers whose cardinal number is 0 or a natural number. In other words, we can count how many elements are in a finite set. Maybe I have the set A has the elements 1, 2, and 3. This has a cardinal number of 3, and so this would be a finite set. The set B equals 2, 4, 6, 12, and 14 is also a finite set. Now the ... are called ellipses, and it means I'm skipping some numbers, but I'm going to follow this same pattern. So here, our set B would be 2, 4, 6, 8, 10, 12, 14. That's 7 elements. I can count the number of elements, so this is a finite set. Any set that is not finite is called infinite. This is a set whose elements cannot be counted. In other words, the set keeps going and going and going and going. We talked in our last video about the natural numbers, our counting numbers, 1, 2, 3, 4, and so on. So that and so on tells us that the set of natural numbers is an infinite set. A new set of numbers that I want to introduce to you is called the whole numbers. It's the set W. W is the set of natural numbers as well as 0. And it is also an infinite set because it keeps on going and going and going. It's the numbers 0, 1, 2, 3, 4, and so on. Our universal set, or our universe, is typically denoted with the capital U. This is all of the elements that we are considering in our discussion. We often use what's called a Venn diagram to show our sets and to see how those sets are related. So let's suppose our universe U is the set of all people who live in Massachusetts. And let's let our set F be a female living in Massachusetts. If I want to draw a Venn diagram for these two, first I would draw a rectangle to represent my universe, and you would put the U somewhere in your rectangle. Then I would draw a loop to represent F, the set of the females living in Massachusetts. Now, because the females are in Massachusetts, notice that my loop is inside of that universe. Now, outside that loop F would be the males living in Massachusetts, and this would be the complement of set F. You'll see our Venn diagram here, and notice that the outside of F is shaded for our complement of F. So our complement is an A with a line over it. It's read the complement of A, or sometimes A complement. And it's the set of all elements in the universe that are not in set A. So A complement is X such that, remember that bar means such that, X is an element of the universe, and X is not an element of A. The slash through that element symbol means X is not an element of A. So let's find some complements of some sets. Well, let's suppose our universe is the letters A, B, C, and D. Set B is the letters C and D, and I want to find B complement. So B complement is everything in the universe that is not in set B. Well, A and B are in the universe, but not in set B. In part B, our universe is the set of N, or the set of natural numbers. Remember, natural numbers are 1, 2, 3, 4, and so on. If we let set E be 2, 4, 6, 8, here we're asked to find our complement of E. Well, I notice that E is the even numbers. So the complement of E would be our odd numbers, 1, 3, 5, 7, and so on. Our next topic is what we call a subset. Now, a subset is written with looks like a C, and you'll notice the line underneath that symbol. If A is not a subset of B, then we put a slash through our subset symbol. Now notice this definition has that line underneath. The line underneath that C allows our two sets to be equal, possibly. So what that means, if A is a subset of B and B is a subset of A, then the two sets have to be equal. They have to be the same set. Now we also have what's called a proper subset. You'll notice as I write my symbol, I do not put the line underneath it. So I know in this case that B cannot be the same thing as A because I don't have that line like we're used to an equal with like a less than or equal to. Notice here in the Venn diagram that we have a dot in A. That represents that there's some element in A that's not in B. So how do we write subsets? How do we know if things are subsets? Let's look at the next example. We have set A is the numbers 1, 2, 3, 4, and 5. And set B includes the numbers 1 and 3. Part A asks, is B a subset of A? The answer here is yes, because all of the elements in B are also in A. Part B asks, is B a proper subset of A? Well, a proper subset means B is a subset, but A has an element that B doesn't have. So here, yes, B is a subset of A, and set A has at least one element that set B does not have. How many subsets does a set have? Depends on how many elements a set has to begin with. So how can we find some other subsets? That's what part C ask us to do. Remember, A is the elements 1, 2, 3, 4, and 5. Well, I could have a subset with just one element. Maybe I choose the number 1. Or I could have a subset with 2 elements, like 1 and 2. Maybe I choose a subset with 3 elements, 1, 3, and 5. Or 4 elements. Now, by the way, A is a subset of itself. So notice here, I wrote 1, 2, 3, 4, 5. This is still a subset of our set. Well, maybe I think I used too many 1s here. Could I use something else? Sure. Maybe I have just 2. Maybe I write the even numbers. Or maybe the last 3 numbers. Or maybe I skip the number 3. You'll notice there are many, many ways that we can write subsets. One other subset I want to talk about is the empty set. The empty set is a subset of every single set.